Today we have Mike. He'll be talking about Steiner tree augmentation problem.
Yes. All right. So yeah, hi everyone. I'm Mik. I'm a fourth-year PhD student in Tepper, and I'll talk about Steiner tree augmentation problems. And this is joint work with my Professor Ravi, and a fellow Tepper student, Wei Zong. So generally, the area that I'm studying is network design or network connectivity. So here, this is a given network, and as you can see, there's a bridge edge. So we're interested in connectivity of this network, and the removal of this dashed edge disconnects the graph, which might be problematic. You might want it to be more robust. But if I augment the graph by adding in the blue dashed link, then it becomes what's called a two-edge connected graph, which is a graph which is connected after any edge is deleted. Yeah? Share screen. Did that work? Cool. Minimize this. So yeah, that's connectivity augmentation. Maybe I start with a two-edge connected graph. It's already two-edge connected, so it has some robustness to edge failures, but I want it to be even more robust. So I might want it to be three-edge connected. And these dashed blue links are links that I can potentially add into the graph, and I have to pay their associated cost. And the goal is to make the graph a three-edge connected graph by adding in a cheap subset of the blue links. So if I add in these two links, the ones of cost 6 and 7, then it becomes a three-edge connected graph. Right, so yeah, the goal in connectivity augmentation is to cheaply boost the connectivity of a given graph, or the edge connectivity of a given graph by 1. So there's okay, so that's connectivity augmentation generally. I'd like to focus on a seemingly very special case of that, which is where the original graph you're trying to augment is actually a tree. So in tree augmentation problem, we're given a tree, so we're given a graph and a spanning tree, and you can add in the links. Each of them have an associated cost, and the goal is to choose links and add them to the tree so that it's now two-edge connected. So it's basically, yeah, just the connectivity augmentation when the original graph is a tree, but actually this seemingly special case is more general. So in general connectivity augmentation, say I want to augment a k-edge connected graph to be k plus 1 edge connected, then that problem reduces to tree augmentation problem if k is odd. So if I want a 5-edge connected graph to be 6-edge connected, that reduces to tree augmentation. And if k is even, you reduce to something else called cactus augmentation. And these reductions are approximation preserving as well. So this is a pretty important problem, especially since in a lot of network design problems, one of the subroutines in the algorithm is an augmentation step. So yeah, tap is a pretty important problem. And one thing I wanted to just point out to get a bit of a flavor. Oh, yes.
If you want to augment connectivity by 2, is that you just do it twice, or that's a different problem?
That you could do it twice, but that wouldn't be the best approximation ratio. There's a way to do that globally and get an approximation ratio of 2. Yeah. Yeah, good question. So to get a bit of a flavor for tap, I wanted to point out that it's actually a covering problem. So let's imagine we're trying to augment this tree. The black edges are the tree, and we can potentially add in these blue links. Well, each link that I might potentially add to the tree induces a unique cycle in the tree. And so yeah, so like this. And if I add in, this link over here, then by deleting any of the edges in this cycle that it induces, it will remain a connected graph. So we say that the edges in the cycle are covered by adding in that link. So yeah, the tree augmentation problem is essentially covering the edges of the tree by these cycles. Okay, so it is a covering problem. Okay, and finally, there's a relatively simple two approximation for this problem, which I wanted to go through, which will actually come in handy later. But before I describe the two approximation, we need to talk about things called uplinks. Okay, so let's say that the given tree is rooted at some node. Let's call it R. Then an uplink is a link which joins a node to one of its ancestors. So it's a link that joins a node to its ancestors. This is an uplink. All of the other links in this graph are not uplinks. And it turns out that in the tree augmentation problem, if all of the links are uplinks, you can solve the problem exactly. This is polynomial time solvable. You can use dynamic programming. That's one way to do it. Another way is the LP relaxation actually is an integral polyhedron if the instance only contains uplinks. So you can solve those instances exactly, and you can actually leverage that to get a two approximation for general instances. So let's say I have a general instance of tap. I'm going to transform it into an instance with only uplinks. So this might be, my given instance. I'm going to essentially take every link which isn't an uplink and break it into two links, each of which is an uplink, and together they cover the same edges that the original link covered. So basically a link joining U and V, I'll get two uplinks, one from U to the least common ancestor of U and V, and one from V to the least common ancestor of U and V, and they have the same cost as the original link. Okay, so now I can solve this new instance exactly. And if I take either one of the uplinks corresponding to a link, I'll take the original link. And this will give a two approximation, because if I have any solution in the original graph, there is a solution costing at most twice as much in the new instance. And I can solve, and I can get the best solution in the new instance. So this is a simple way to get a two approximation. But okay, so this is a two approximation. The problem was introduced in the 1980s, and until very recently, the two was the best known approximation ratio. But yeah, major breakthrough recently. I think they actually give a talk here at one of these theory lunches. Traubens and Klusin managed to get a better than two approximation for the tree augmentation problem. And they get 1 plus ln of 2 plus epsilon, and then very quickly afterward, bring it down even further to 1.5 plus epsilon. And they use what's called a local greedy algorithm, which I'll go into a bit more later. But yeah, this was a major result, and the idea of our problem we were interested in is, can we use the new ideas to improve upon network design problems using their ideas and get improvements? Okay, so now I'll talk about the problem we're actually studying, and that's called Steiner tree augmentation. So it's tree augmentation, but instead of augmenting a tree, you're augmenting a Steiner tree into a two-edge connected Steiner subgraph. So it's a generalization of the tree augmentation problem, and formally we can say we're given a graph and a subset of nodes, which I'll call terminals. These are called the terminals that I need to connect up, and we're given a Steiner tree which connects the terminals. For example, if the blue nodes are terminals, the black tree is a Steiner tree on those terminals. And then we have costs on links. And again, we need to add in links and now potentially nodes because it's not a spending tree anymore. We might involve nodes in the augmentation and add them to the graph so that it's now a two-edge connected Steiner subgraph, which means that if any edge is deleted, there's still a path between any pair of terminals. Okay, so this is the problem that we're studying. But maybe before I go further, there's a very quick simplification that you can do on this problem, which makes it easier to think about. So if I'm looking for a two-edge connected Steiner subgraph, that has two-edge disjoint paths between any pair of terminals. But actually, since we're focusing on two-edge connectivity, you can say that a minimal solution to this problem is a genuinely two-edge connected subgraph. So it will actually have two pairwise edge disjoint paths between any pair of nodes, not just terminals. Yeah, intuitively, you would never include a Steiner node, which isn't involved in a path between terminals. So that also has two connectivity on it as well in the case of two connectivity. So using this, you can make the problem a bit simpler by assuming that the given tree, all of its nodes are terminals. Okay, so we're given a tree and all of those nodes are terminals, and then we just need to add in links and nodes so that it's now two-edge connected. Okay, so this is the problem. Just a couple of examples. So if this is the tree and we're seeking to make it two-edge connected, I could add in these orange links and it becomes two-edge connected. Okay, yeah. Another example which kind of illustrates things is I could take this large component outside the tree and add it in, and has the effect of joining up 3 nodes rather than 2, which occurs in the case of normal tree augmentation. And then I can add this one and it'll become two-edge connected graph. Okay, so what is known about Steiner tree augmentation problem? So you can directly apply an algorithm for the very general problem of survivable network design to get a two-approximation for this problem. Most edge connectivity problems in network design, you can just use survivable network design and get a two-approximation, but the key is, can we do better than 2? And the question is, can we use their ideas and breach the barrier of 2? So we basically, yeah, we do this. We match the results for tree augmentation problem for the generalization of the Steiner tree augmentation problem using the local greedy algorithm. So I will explain a bit of how we do that. First, first it would be helpful to go over a bit of how the local greedy algorithm works in just the tree augmentation problem, and then talk about like what hurdles come up when you're dealing with Steiner graphs. So the local greedy idea is to start off with the simple two-approximation that I described earlier, and then make iterative improvements using local moves. In this case, a local move is just adding a subset of links to the graph and then dropping links which are rendered not necessary anymore for feasibility. Okay, so yeah, we will start with the two-approximation, which uses uplinks. And then we'll just keep, and this is why it's called local greedy. We'll choose the best local move. We'll choose a subset of links, which maximizes the weight of uplinks that I'm allowed to drop by adding in those links over the cost it incurs to add in those links. Okay, so I want to reduce the cost as much as possible in my drop after I add in those links, but I don't want to pay that much. Okay, so once I've picked the best such subset, I'll add it to my solution and drop the uplinks that are no longer necessary. And then you just keep doing this until there's no local move that improves things, another way of saying that is there's no uplinks left. But this is, okay, so this is not quite right because the maximization problem here is not solvable efficiently. You can't actually choose a subset of links to add maximizing this ratio over all subsets of links. But the very nice idea in Traubin's and Cluson's algorithms is they define a restricted class of links called k-thin subsets, which you can efficiently optimize over, and they're general enough so that there's always a local move if the solution isn't if the solution is costly. Okay, so the formal way to say this is encoded in this decomposition result that they show, which essentially it's kind of wordy, but the upshot of it is that any solution to the tree augmentation problem can be partitioned into k-thin components for constant k. If we want to, for any epsilon, it can be partitioned into k-thin components, and almost all of the weight on the uplinks can be dropped by adding in some part in that partition. So all but an epsilon fraction of the weight of the uplinks can be dropped by adding in some part. Okay, yeah, but it's not too necessary to understand this in detail. The main point is that the decomposition result is the thing that says that if the solution is costly, I can always find an improving k-thin component to add in. Okay, so essentially, to use the local greedy algorithm, the two ingredients is I need to have a structured two approximation as my initial solution, and then I need to describe a local move and a decomposition theorem, which shows that you can always make it an improving move. So the first thing I'll talk. The thing I just described is enough to get the 1 plus ln of 2 plus epsilon approximation. And then after a bit more tweaking, you can get it down to the 1.5, but I'll just talk about the 1 plus ln of 2 in this talk because it's simpler. Okay, so I'll first talk about how we get this uplink 2 approximation in the case of Steiner tree augmentation. Okay, so actually, let me, is there any questions so far? The general outline clear? Okay, so yeah, I'll talk about how we do the 2 approximation for STAP. Just to reiterate, like there is a 2 approximation using survivable network design, but that will give a non-structured solution. We want a solution which only involves uplinks, because that's where the decomposition theorem holds. So, okay, so in order to get that, we have to do a bit of pre-processing on the instance. So we can basically assume metric completion. Okay, so what do I mean by this? I will assume that there exists a link between every pair of terminals. Okay, if there's no link between a pair of terminals, I will add in a link with length or with cost equal to the cost of the shortest link path, shortest path in the link graph, so not using edges in the tree, and add that in, and you can assume that those exist, because if I ever take one of these, instead I can take the path, and this will cost as much. Okay, so we assume that metric completion has been done, and then another sort of completion operation you can do is called shadow completion, where if a link in the graph exists between 2 terminals, I'm also going to assume that all shadows of that link are also present. So what do I mean by a shadow? Essentially, okay, so a shadow is if a link joins, let's say this link of cost 4, U and V, then I'll also assume there exists a link between any pair of nodes on the path between U and V. because that link would merely cover a subset of the edges covered by the original link. So a shadow is essentially a link which covers just a subset of the edges covered by the original link. And so we can assume those exist, because if you ever take one, you'll just take the original and that will cover at least as many edges. Okay, so, okay, we assume that shadow completion has been done as well. And now we will, use this to give a two-approximation. So focus on the optimal solution to Steiner tree augmentation problem, and also a specific component. Okay, so that was a bit too early. Focus on one connected component of a solution to the Steiner tree augmentation problem. Let's say it's this orange component. So what I'd like to do is show there's an uplink solution of at most twice the cost. So what I will do is take an Euler tour of this component. It's a tree. I will take an Euler tour of this tree, traversing every edge exactly twice and returning back to the starting vertex. So just pick any starting vertex, take an Euler tour, traverse every edge twice, and come back. And this induces an ordering on the terminals. Okay, yeah, so I have it here. So if I take the Euler tour, there's an ordering of the terminals which are visited. Okay? And instead of taking this entire path between the terminals, I can utilize the fact that we did metric completion and instead take the direct link between the first terminal visited and the second one, and then the second one to the third one, and essentially create a cycle on the terminals. And each of these links costs at most the path between them, right? So this link costs at most this one costs at most this, and this link costs at most the length of this path. So overall, I've gotten a solution covering the same tree edges, which only uses links between terminals, and it costs at most twice as much as the orange solution. But we needed uplinks, so there's one more thing we need to do.
Simplified version of Christopher's algorithm, right?
Yeah, it's very similar to the Christopher's algorithm. Yes. But yeah, still we don't have uplinks. All we've done is show that you can use links between terminals. But we want uplinks. So the idea is now instead of going from 1 to 2, 2 to 3, 3 to 1, we will use half of each of those. Okay, so instead of going from 1 to 2, I will go from 1 to the least common ancestor of 1 and 2. Then instead of going from 2 to 3, I'll go from 2 to the least common ancestor of 2 and 3. And then from 3 to 1, I'll go from 3 to the least common ancestor of 3 and 1. And okay, so I can do that. It's not clear that that's still feasible, but using shadow completion, I mean, it is still at most twice the cost, because each of these links are shadows of the links that go directly between the terminals. Okay, so that exists. And then the reason why this is still feasible is essentially, okay, so focus on deleting any edge. The Euler tour goes from some terminal and returns back. And what you can show is that that edge partitions the terminals that were traversed in the tour into two halves. And when it goes from the left half to the right half, it will cover the edge, or it will cover the edge when going from the right half to the left half. Okay, so at a high level, the fact that the Euler tour goes back and forth across this cut means that one of the two halves will be responsible for covering the edge. Okay, so this is how we obtain an uplink solution which has almost twice the cost, and we can use that in the local greedy algorithm. Yeah, we just need to describe how to do a local move now. But yeah, any questions about the two approx? Cool. So we have the uplink two approximation, and now we need to talk about the local moves. Okay, so this is where we introduce something called hypertap, which I kind of alluded to earlier, where a component of a STAP solution now doesn't necessarily have the effect of joining just pairs of terminals, but it might join arbitrary subsets. So if I look at this orange STAP solution, the orange component, each of the components in that solution has the effect of joining some terminals. And what edges are covered by joining these terminals? So this solution, this orange piece joins these three terminals, and all of the edges in the subtree, which is rooted at the least common ancestor of those terminals that I joined, are covered by joining that set. Okay, so by adding that orange piece, you cover that entire subtree. So while in TAP, you were adding things and this covered paths in the tree. Now, if you look at hypertap components or just STAP components, it covers trees, subtrees of the given tree. Okay, so yeah, it's kind of just like TAP, but you can join arbitrary subsets of links. So formally, you can define hypertap where you're given a tree, and now you're given hyperlinks, which are just subsets of tree nodes. And each of the hyperlinks covers the subtree rooted at the node, which is the least common ancestor of the nodes it joins. And then the goal is to pick the cheapest subset of hyperlinks to cover all the tree edges. Okay, so in theory, there's a hypertap instance which is equivalent to any STAP instance, because in STAP I have to basically do two things. I have to decide which nodes to join up, and then also how to join them up in the best way possible. So the hypertap instance kind of encodes which nodes I should join up. Okay. Okay, so hypertap encodes which nodes to join up. There's the question of how best to join up a given set of terminals. So let's look at this. If I have the orange component, that has the effect of joining up these three terminals. But if let's focus on some subset of terminals, how can I find the cheapest component which has the effect of joining them? Okay, so what I would like to do is find the cheapest component joining every subset of terminals, and then put in a hyperlink joining those with that cost. Okay, so but this seems challenging. So actually, this is sort of an interesting point. If I'm looking for the cheapest subset joining some set of terminals, that's itself a Steiner tree problem, right? Because I'm trying to join up a given set of nodes, and I have to use the cheapest subset of links to join them up. So this is essentially still a Steiner tree problem on the graph, which only uses links. So the costs are the links, and I'm looking to join up those terminals. But Steiner tree isn't solvable. I mean, this is you would need to use an approximation, which is kind of it's kind of a hurdle if you're trying to reduce the hypertap. So what we do to deal with this is utilize an old result on Steiner trees, which allows us essentially to focus on solutions which only join constantly many nodes. Okay, so this is called gamma restriction. So I'll call a solution to STAP gamma restricted if all of the components join at most gamma nodes. Okay, if opt gamma is the cost of the cheapest gamma restricted solution, then you can you can use an old result on Steiner trees to show this for STAP as well. So for any epsilon you want, you can pick a large enough gamma so that if you restrict to gamma restricted solutions, the cost of the optimal gamma restricted solution is barely more than the optimal overall unrestricted solution. Okay, so this allows us to essentially, with loss of an arbitrarily small constant, focus on finding the best gamma restricted solution. Okay, so now that we know that we just need to find gamma restricted solutions, every full component joins constantly many nodes. And actually Steiner tree can be solved exactly if the number of terminals you're interested in joining up is constant. Okay, so it's called fixed parameter tractable. There's an algorithm which solves Steiner tree in time n cubed 3 to the p, where p is the number of terminals. So given that p is a constant now, this is a polynomial time operation, and we can efficiently create the equivalent instance of hypertap for our given stap instance. Okay, and by the way, this is, I think this has been improved from n cubed by now, but this is kind of the old result, and it's all that's really necessary. Yeah, so we can perform the reduction efficiently. And so what's the point of all this? Essentially, what we needed is a local move with the decomposition result. And the next thing, so what we did is the decomposition result for tree augmentation can actually be generalized to the setting of hypertap as well. So fully general hypertap, if you have any uplink solution, so I have a tree, I root it somewhere. If I have any uplink solution, any solution to hypertap can be partitioned into k-thin components, and for at most an epsilon fraction of the weight of the uplinks, you can add in some component to drop each of those links. So we will leverage that to get the local greedy algorithm and the approximation guarantee. So overall, the algorithm is start with the two-approximation, which uses uplinks, and then now just compute the equivalent instance of hypertap, and in each iteration choose a k-thin component of hyperlinks now to add to the solution, and drop the redundant uplinks. And again, you want to choose, the best k-thin component of hyperlinks to add, and we show, just like in tap, you can do that efficiently in hypertap as well. Yeah, to maximize the ratio of the drop links over the cost I incur by adding them. So keep doing this, drop the links, add that to the solution, and continue until there's no improving move. And by the same analysis that they did for tap, this results in a 1 plus ln of 2 plus epsilon approximation for Steiner tree augmentation. Okay. So yeah. So that's pretty much it. I wanted to point out some notes. So how do we get that down to the 1.5 plus epsilon approximation? So the idea here is, in the original analysis, we're only dropping uplinks in the initial solution. But you may want to also drop links which were previously added in the iterations. So by doing local moves, I add in links. Maybe I want to drop links that were added in some earlier iteration. So you can break each link down into uplinks and consider those new uplinks also being dropped. And then this brings it down to the 1.5 approximation. Okay, so, and then another thing is, okay, what about higher connectivity? So in the tap setting, if I wanted to make a k-edge connected graph, k plus 1 edge connected for k odd, that reduces to tap. So is the same thing true for Steiner trees? Okay, so this is a bit more subtle because we were specifically using the fact that we were going to a 2-edge connected subgraph. Remember, I was saying like a 2-edge connected Steiner subgraph is genuinely a 2-edge connected graph. but that only holds for 2. So this doesn't immediately work. If I want to make a k edge-connected Steiner subgraph into a k+1 edge-connected Steiner subgraph, this does not reduce to Steiner tree augmentation, but a much less general problem of just taking a k edge-connected graph and adding in nodes as well as links to make it a k+1 edge-connected graph. That reduces to Steiner tree augmentation problem, as opposed to just augmenting a k edge-connected graph to a k+1 edge-connected graph just by adding in links. Okay, so now you can use nodes in the augmentation. Okay, and then finally, since we're using nodes in the augmentation, you might ask for what if the nodes had weights as well? Okay, so we were focusing on just the links having weights, but if you in the node weighted case, you can get a O of log of the size of the given tree approximation for Steiner tree augmentation where the nodes have weights, and having nodes have weights generalizes having links have weights, because if a link has some weight, you can just subdivide it by putting a node in the middle and give the cost of that link to the node and solve the instance of node weighted stuff. So this is much more general than the edge weighted case, but we get a lot worse of an approximation. All right, that's it. Yes.
Maybe I missed something. Do you know any lower bound of the achievable approximation?
For
Like assuming it is that-
yeah. So the only thing I know for the only thing that is known for TAP is that it's APX hard. So I don't know the exact constant, but there is a constant so that you can't approximate it below that constant. And then it's also NPR on a good number of pretty special cases. So like TAP for stars, if the tree has like height 1 is solvable, that's actually just edge cover. But as soon as you go to depth 2 trees, that's NP hard already. It's NP hard. It's NP hard if the links forms a cycle on the leaves of the tree as well. Yeah. So yeah. Oh yeah, actually, another thing that I think is interesting to point out here. So I mentioned that TAP is a covering problem. And if you write down the natural relaxation, so the covering LP relaxation for that, you could ask what the integrality gap is of that relaxation. And it's known that that's at most 2, so there's a 2 approx, but it's at least 1.5. So these new results on TAP kind of show that if you want to beat 1.5, you can't use the natural LP because there's an integrality gap of at least 3/2. So we already have a 3/2 approximation. If you want to do any better than that, you'd have to use a strengthened LP or just not use LPs at all. Yeah. Yes.
So I have a question regarding the gamma restriction part.
Okay. Yeah.
So I saw here that basically gamma has to grow exponentially with 1/epsilon.
Yeah.
And if so, can we find a good OPT gamma in like efficiently?
Okay. Yeah. It's true that if you want to preserve the approximation ratio to a factor of 1 plus epsilon, the gamma you have to choose depending on epsilon is 2 to the ceiling of 1/epsilon. So yeah, it's exponential in 1/epsilon. And then you're asking, can we find opt sub gamma efficiently? Yes. So yes, you can. That's essentially what we do. So after this step, we can focus just on finding the optimal gamma restricted solution. And the fact that the full components now join constantly many. So when I say constant, you're right, it's exponential and epsilon, but it's independent of n, right? So you just treat that as for any constant epsilon, that now gamma is a constant, right? So it doesn't matter if it's exponential and epsilon, gamma is a constant. You join at most gamma terminals in each full component, and that allows us to, efficiently get the equivalent hypertap instance. So yes, you can efficiently compute, approximately the optimal gamma restricted solution. Yes. Mhm.
I see. Thank you.
Yeah.
So just to clarify, the running time, the overall algorithm would be
Hmm.
polynomial and then a double exponential whatever. The exponential
Hmm.
dependence on p here and p itself would be exponential dependent on one.
Right. Yeah, that's right. But actually, it's at least that. I think there also may be n to the 1 over epsilon. Like I would have to think about that. So yeah, it's definitely it's definitely one of those algorithms which it has a very large exponent, but is polynomial. Yeah.
This thing.